Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Okay, let's unpack this. We're doing a deep dive into the absolute backbone of the modern internet. It's a concept we use every single millisecond, but rarely ever stop to actually examine. I'm talking about the IP address. I mean, if you think of data as a package, the IP address is basically its precise numerical label. It's like a virtual postal code that identifies both the sender and the intended recipient. It just makes sure data gets where it's going.
Exactly. And that whole process is governed by the Internet Protocol. The full name is Internet Protocol Address, or sometimes you'll hear IP number. Its job is really to define the formats for addressing and, for packaging those data schemes. But, and this is a crucial point, the IP itself doesn't guarantee delivery. That's where something called the Transport Control Protocol, or TCP, comes in.
Ah, so they're two halves of a whole.
Precisely. The TCP/IP suite. You can think of it like this. The IP labels the package, and TCP makes sure it actually gets there, and gets there intact. So our mission today is to sort through all of this. We want to go beyond the simple definitions. We're going to explore the four main categories: public, private, static, and dynamic, and then get into some of the more specialized types and versions that are, well, literally holding the internet together.
Excellent. And I think the clearest way to start sorting through all this complexity is by location, right? The boundary between your home network and the entire outside world. Let's start inside the firewall. Let's talk about the private IP.
Good place to start. A private IP is the unique number your router assigns to every single device inside your local network.
Every single device.
Every single one. Your computer, your tablet, your smartphone, and now, the huge number of IoT products, your smart speaker, your fridge, your thermostat. Each one gets a unique internal ID so it can talk to the router.
And these are the addresses that usually start with something like 192.168 something something, correct?
That's the one. And they are unique only within your home. What's fascinating is that your home network can use the exact same private addresses as your neighbors because they never talk directly to the outside world.
Okay, so if that's the party happening inside the house, how does the internet know where the house is? That's where the public IP comes in, I assume.
Precisely. The public IP is that single primary address for your entire network. Your internet service provider, your ISP, gives it to you. This is the address that the rest of the world sees.
So when I go to Google, my computer's private address isn't what's being sent out?
No, not at all. Your router uses a process called Network Address Translation, or NAT. It's really clever. It swaps the private IP of your computer for the single public IP of your router. When the data comes back from Google, the router remembers which internal device asked for it and forwards it along.
So the router is the translator. It's the gatekeeper that manages everything.
That's a perfect way to think about it,
Yeah.
yes.
All right, so now that we've established location inside versus outside, we should talk about permanence. This brings us to the whole dynamic versus static IP address question.
It does. And for nearly every residential user listening right now, you are almost certainly operating with a dynamic IP.
And these addresses are temporary, right? They're constantly changing.
Constantly. They get allocated every time your device connects to the network, or they expire after a set amount of time.
Why is that the default? Is it just about managing resources efficiently?
Absolutely. It's really the difference between renting and owning an address. ISPs have a large shared pool of addresses, and a dynamic host configuration protocol server, a DHCP server. You can think of it as a loan officer. It just leases out these IPs for a fixed period.
So it's cheaper for the ISP.
Much cheaper, more efficient, and it actually provides a decent layer of obscurity for you, the user, because your public face changes from time to time.
That makes a lot of sense. So if dynamic is the standard, when would someone, maybe a business, want a static IP? One that stays the same for years?
You'd want a static IP if you need guaranteed remote access. Or if you're running a service that has to be permanently findable at one specific address, think about things like corporate VPNs, web servers, email servers, that sort of thing. If their address was constantly changing, those services would just break instantly.
But there has to be a downside to that permanence. I mean, if your address never changes, you become a much easier target, don't you?
That is the crucial trade-off. A static IP is fixed, so it's easier to trace, easier to geolocate. And it's a much more stable target for malicious actors looking to launch, say, denial of service attacks. Companies pay a premium for a static IP, and they often spend a lot more on security because they are sacrificing that little bit of security you get from a constantly changing dynamic address.
That concept of needing a static address for a server leads us right into the world of websites. And here, we get the difference between shared and dedicated IP addresses.
Yes. So when a small business is just starting out, they almost always go for a shared IP address.
Can you detail how that works? And more importantly, what are the risks?
A shared IP is exactly what it sounds like. It's a single IP address that hosts multiple domain names, so multiple websites, on the same server. It's cheap, and for a small site with low traffic, it's usually fine. The drawback, though, is huge. It's a shared reputation risk.
Meaning if one of the other 100 sites on that IP does something bad.
Like sending spam or gets infected with malware, yes, then that entire IP address can end up on various internet blacklists.
And suddenly your completely legitimate business website or your emails start getting blocked or penalized just because of your bad neighbor.
Exactly. That's why a dedicated IP address is really the way to go for any serious commercial operation. It guarantees that your IP address is uniquely assigned to your domain and your domain alone. It reinforces reliability, and it has a major practical benefit.
Which is?
You can access your site using just the numerical address. This is incredibly useful for testing or during a domain transfer, to make sure there's zero downtime.
Okay, this is great. Let's switch from operational choices to infrastructural necessity. We have to talk about the version crisis that really defines the modern internet, IPv4 versus IPv6.
Ah, yes. This is where it gets really interesting and, frankly, a little bit frightening. IPv4 was the original. It was deployed way back in 1983. It still carries something like 94% of global internet traffic today. But it was designed for a world with, a few mainframes and a handful of universities, not billions of smartphones.
The limitation is just built right into the math, isn't it? IPv4 uses a 32-bit address scheme, and when you do that math 2 to the power of 32, you get just over 4 billion unique addresses.
4.29 billion, yeah. Which sounded like a vast, endless number in 1983. But as soon as smart devices exploded and entire continents started coming online, those addresses just vanished. We officially ran out in different parts of the world starting a decade ago.
So IPv6 was created to solve this scarcity problem.
It was initiated way back in 1994 to solve this exact issue. And the scaling jump it's just incredible. It's not a little bigger, it's astronomically larger.
This is the ultimate aha number for anyone learning this stuff.
It really is. IPv6 uses a 128-bit address space. So instead of 4 billion, this allows for 340 undecillion unique addresses. I mean, that number is so large, it basically guarantees we will never ever run out again, no matter how many IoT devices we connect.
Okay, so if IPv6 is the definitive solution, why are we still so heavily reliant on the old, limited IPv4? Why is adoption still such a struggle?
Two main reasons, really. Infrastructure cost and backward compatibility. Think about it. Every single router, every server, every piece of network gear installed for the last 30 years was built for IPv4. Migrating all of that requires huge amounts of money. And until recently, most networks just used clever workarounds like that NAT process we talked about to stretch the use of the few IPv4 addresses they had.
That transition from a small set of addresses to this massive near infinite pool brings us to our final and maybe most complex layer, the operational characteristics. So once we have the address, how does the data actually find its target efficiently? We're talking unicast, broadcast, multicast, and anycast.
Right. Unicast is the simplest one. It's your standard web browsing. It's one-to-one communication, a single sender talking to a single receiver. It's the default in both IPv4 and IPv6, and it handles, the vast majority of traffic.
Next up is broadcast, which is an IPv4 only thing, right? A bit of a relic.
It is. Broadcast lets you send data to all devices on a local network at once with a single transmission. It's useful for some older network discovery things, but it's incredibly inefficient. It's noisy. It forces every single device to process the packet, even if it's not for them.
So IPv6 just got rid of it entirely.
They did. They abandoned it.
And what did they replace it with? That must be multicast.
That's multicast. It's the refined, intelligent solution. It's still one-to-many communication, but it's smart about it. Data is sent to a specific IP multicast group address, and the network routers only forward copies of that packet to devices that have explicitly subscribed to that group.
So if you're streaming a live football match, you don't send a separate stream to every viewer.
Exactly. That would be a unicast nightmare. Instead, you multicast it. And only the devices that are actually tuned into the game receive the packets. It saves an enormous amount of bandwidth.
Which brings us to the most sophisticated method of the bunch, Anycast.
Anycast is fascinating. It fundamentally changes the logic of the destination. With Unicast, you're going to one specific host. With Anycast, you send a packet to an address that is shared by multiple hosts, often all over the world. And the network itself decides which of those hosts is the closest or most efficient destination for that specific packet.
And how does the network define closest? Is it just about geography?
It's usually latency-based. It's driven by dynamic routing tables, specifically using something called the Border Gateway Protocol, or BGP. A classic example is a global DNS system. When you type in a website, you need that address to resolve fast. So companies like Google advertise the same DNS server address, 8.8.8.8, from hundreds of physical locations. Anycast and BGP work together to make sure your request goes to the nearest physical server that's responding to that address, which minimizes your latency.
So what does this all mean for you, the listener? We started by defining the IP address as this foundational identity layer for the internet. We cut through the location logic public for the outside world, private for your own devices, and the operational logic dynamic for most of us, static for services that need to stay put.
And we learned that the modern world just requires this astronomical scale. We had to make the jump from IPv4's 4 billion addresses to the 340 undecillion of IPv6, even if that migration is still ongoing. What's truly remarkable is that this simple numerical label defines so much more than identity. It defines these sophisticated routing strategies, from the simple one-to-one of Unicast to the bandwidth saving of multicast and the incredible load balancing of Anycast.
It really is the unseen engine of connectivity. So we discussed how a static IP, because it's permanent, makes it much easier to procure information about a device. Now think about the rise of the Internet of Things and the fact that a private IP is assigned uniquely to every single smart device in your home, every sensor, every speaker, every camera. How might the ability to procure information change if those private IPs somehow became stable or maybe externally accessible? How would that change the way we think about the privacy risks of our ever-growing network of always-on smart devices? Something to consider next time you install a new gadget that gets its own little numerical ID.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo, haven't you checked out our new book yet? Link in description.